Yet another presentation about monitoring. The aim of this presentation is to give you a practical examples of how to monitor Lustre to maintain optimal performance in a bulk I/O scenario. Let me talk you through the agenda. I split the presentation in 4 steps. Firstly, I will guide you through the huge amount of metrics that we can find inside the profile system of Lustre. Then I will show you some tools that administrator can use in problem solving. Finally, we will see a practical example of how to use metrics and tools to analyze the workload of an application. Monitor a Lustre file system is essential. The amount of statistical information is really incredible and give to the administrator the opportunity to answer all the questions coming from users. But also you have the chance of lost in the proc file system. Questions like who is overloading the file system, why my application is so slow, why the file system has a regression in the performance could be addressed if an administrator choose the right tools and know the Lustre metrics inside the proc file system. So the first indicator of the health of our system is the bulk I/O rate. As we saw yesterday, the read bytes and write bytes are a very easy way to achieve this goal. It's the first indicator. And the developers of Lustre give us some tools to manage these files. Yes, you can cut the file as you want, but if you use LLStat, you can achieve better results. At the same, for example, you can put the LLStat output on a file and use GNU-plot to write your data. LLStat has some funny option. For example, you can interactively see what's going on your file, and you can use LLStat to many of the stats information again the proc file system. Another important metrics is the stats inside each OSS. These stats give you more the operation that the OSS is doing. And this is changed in 2.4, the BRW stats. It's changed just because now is a link to the LDISC-FS backend, because you could have different backend. You can have ZFS backend, so for consistency, we link this file. And the BRW stats is very important to go deeply in the OST information and give us some very important histogram about what's going on each OSTs. For example, I/O time is the latency of your LUN underline your OSTs. So, for example, if you have a rise of this histogram, probably your LAN is rebuilding something or something wrong is going on. Another metric that is changed is in 2.4 is the stats for each MDT. This is useful to understand how many open, close, MK node and other stuff. And is changed in the name is not more stats, it's MD stats, and in the location, they have the possibility to have more than one MDT. But the historical NDS statistics remain on the same place, and you can have here the metadata operation, I/O operation per second with this information. There are many other metrics. Administrators sometimes would like to understand which client overload the Lustre file system. We saw yesterday that people activate the LNet debug on the client. I prefer to follow a presentation that Damian has given in last year during this LAD and activate the request buffer history on the OSS and the MDS and make a little script to understand who is the client that make more activities. It's up to you. We have talked a lot about monitoring tools, but I want to show you something that are inside Lustre. The plot LL_stat is a very easy tools that are inside your Lustre installation. You can use this to extract information from a log that you create with LL_stat, and you can use it to import the .dat file generated from plot LStat inside your spreadsheet, or use GNU-plot. I'm happy to use GNU-plot. Okay, I have selected four tools to manage the stat. The first tool is, for me, is Python. Other people I know that use Bash or Java or whatever, but the matplotlib is a very cool library to create a chart with Python. It's very cool. This is Andrew Hasselton point me to this library, and it's very cool. It's very easy to implement and give you the opportunity to create a very nice chart. Collector is an historical tool of Lustre. I really don't know if there is some improvement in the support of Collector, of Lustre 2.4 in the Collector, but Collector gives you information on the client that nobody does this. And my preferred tools is LMT for the scalability that have and other stuff. But all these tools have a big problem. The big problem is the real time, because yes, you have LTOP, but LTOP is not easy to give to, for example, a first level of support. Operation guys. So Intel decided to improve the Chroma project from OneCloud and create the Intel Manager for Lustre. Intel Manager for Lustre is a web-based interface, part of the Intel Enterprise Edition for Lustre, and the main goal is to help to manage and monitor a Lustre file system. Managing, it means that with IML you can install, configure not only the Lustre file system, but also the iAvability tool, CoroSync, Peacemaker, and other fancy stuff. We include the Mellanox support, so we provide directly the RPMS of Lustre with for the Mellanox card, and it's something that helps people to install and manage Lustre, but you can use them to monitor also. They is a Django application based on a Postgres database, so you can use in real time you can use in real-time AML to monitor your system and extract from the Postgres database the data for further investigation to understand what's going on. But if you have, for example, on a first level of help desk, a dashboard like this could be useful. This dashboard is in Web 2.0 flavor, so you can drag and drop, make something like this. Here you have the balance, the capacity of each OST. Here you have the name of your file system, the space used, the name used, the number of clients connected, metadata operation, read-write, the object storage server, metadata server, and you can go drill down to each component, and you can see the bulk I/O of each OSTs or the CPU of each system. And another very funny thing is that we have little knowledge on the logs. We configure the syslog to have a single point. The AML will be the single point for all the logs, and we provide some knowledge on this log and give as alerts information, high level of information to the user. But if you want to drill down to the single log, you can do that. For this experiment, this is an information that is very important, because you can have the bulk I/O rate globally, aggregate, or for each OSTs, as we can take from LMT. And this is the metadata operation that we saw in our tools. But unfortunately, I don't have IML available on the system that I have used for my analytics, because I'm using Amazon to run some activities, some experiment. With the help of Andrew Heselton, I have installed the MedBench 2. MedBench 2 is an application where the problem is to generate simulation of the cosmic microwave background radiation sky map. This is the sky map. Each of these simulation involves a very large matrix inversion, and this is why we have some I/O activity on that. We use a Lustre cluster on Amazon to install this tool. The Amazon cluster is an 8 OSS cluster with 16 client nodes. The network is a Ethernet network limited to 1 GB per second, and unfortunately I don't have IML on that, so I use LLTop, part of LMT. GnuPlot has some Python, Matplotlib, NumPy script to analyze the problem. MedBench 2 has a component that grows in a n squared, where n is the number of pixels that I want to achieve from my experiment. It also has an intertask communication that grows as n cubic. We want to know, we want to anticipate how the application scales in this environment, in the Amazon environment, and what is the workload look like. In this picture, we have the time on the y-axis and the number of pixels on the x-axis. The two pictures are the same. I changed the scale, linear scale here and the log scale here. And probably for the log scale, we saw that this application is more on the fit better the n square line when the number of pixels are small or better, and the n cube line where the number of pixels increase. So this application here is more, in this environment, is more I/O bound for the small scale and more network bound for larger number of pixels. And we use LTOP to confirm from the bulk I/O that we receive this number. And this is the results. On the y-axis, we have the performance, megabyte per second. On the x-axis, we have the time. On the smaller experiment, 60 kilopixel, we have an increase of the spikes, and in the 32 pixel experiment, we have 10 spikes because we have 10 beams, and the inter-process communication is the main factor, as you see. You don't see any read because the experiment is not enough to exceed the memory that we have on the clients. So all the reads are locally cached. To avoid this problem, we have to run a larger experiment, for example, 128 kilopixel. And probably this take with 50 hours to complete. Another scenario that we can use for this presentation is another Amazon Lustre cluster based on 16 OSS and 32 clients. We have always LLTOP, Python, NumPy, Matplotlib scripts. And we have a big problem on this scenario. The big problem is that we don't achieve the IOR number that we believe, because we have 60 OSS, so with a Ethernet network limited to 1 gigabyte per second, so we should arrive to 1.8, 1.9 gigabyte per second. This did not happen. I show after the break, I show in my cloud presentation that. And to understand why we don't achieve this number, we use the LTOP recording to understand what's going on. On the y-axis, we have the megabyte per second, and on the x-axis, we have the time. So I measured the peak performance of the IOR run. So as you see, in the first 5-6 minutes, we achieved the performance that we have from the hardware. We achieve likely 1.9 megabytes per second. After that, we have a long tail. And this is the problem. For read, we don't have this problem. We have a little bit lower the performance, but it's normal for Lustre. But the run is more steady. So we need to go a little bit deeply on that. So we try to understand which OSS have a strange behavior. But we saw that all the OSS have the same behavior for writing. A nice limited, hardware limited run for 5-6 minutes, after that a long tail. For the read, we don't have any problem. So we have to go another, another level deep, and we go to understand what's going on the OSTs. And we saw that many OSTs have a good, steady activity, and as with the they achieve the maximum performance that Amazon give for a single ABS storage. But other OSTs has a long tail, and some are steady. Other, when the other OST finish, increase a little bit to the. But what's going on? Why this activity? On the read, we have a completely different behavior. We have speak activity, we have burstly activity in the time. Write, every node that is writing can have 8 outstanding RPC to each OST. During the write, these RPC all arrive and get processor more or less first input, first output. Those all the tasks make steady progress without any task or OST get a lot ahead of any other. For read is very different, because the read benefit from the read ahead. So we can anticipate the client request. So this is confirmed from the BRW stats. If you see the I/O time histogram in the in the BRW stat of each OSTs, you can see that the read are more than 80%, like 90%, as was due from the very first activity, as it's very quickly. The write are very has a bad comportment, and probably because there is more latency on our underlying storage, and the storage that Amazon provides to us is a network-based storage. So this confirms that the latency of the read and the 8 RPC outstanding limit the write activity, and at the other side on the read burstly the read. And you can see in this chart that there are some writes that are steady, other that are really steady, but the performance is very slow, and this is the OST that create the long tail. So the amount of information provided by Lustre can be used like to monitor the health of the cluster. Intel is trying to put on the market a manager tool, a monitor tool that help us in this effort. Our IML can be used real time to monitor the activity of our cluster independently of the underlying storage. But you can also use AML as LTOP, LMT to analyze the data after your experiment using the Postgres database where all the data are stored. Any question? No, IML is not open source. What?
The entire Intel manager for monitoring analytics. Will there be an open source version available later this year or something?
IML will not be open source. The Intel Enterprise Edition for Lustre is a bundle. It is not a single product. And in this bundle, we have Lustre, is exactly the community edition of Lustre, and we put IML, but IML for now is a proprietary software from Intel. We put also other couple of things that are important, like the Hadoop connector for Lustre. Yes, storage API that you can write to manage for IML directly your storage, for example, to create arrays and so without using external storage administration tool.
On your last conclusion slide, you also wrote that you analyze data. Is there also some feature to do like real time series analysis? Because what you basically collect is a time series. So do you also run some data mining algorithm to like extract a trend in the data or noise or whatever? Like for instance, you could, I mean, this is just some future. So you can collect, let's say, data for a couple of months and then analyze this kind of data. And when you have this failure, this data is usually latent or hidden in this kind of trend. Are there any like thoughts from Intel to go in this direction? So business analytics or data mining. So like to put it one step forward rather than saying, okay, this is a peak. I assume this is something is wrong or something is going on.
Allora, at the moment, IML don't provide any business analytic stuff. But the database is a Postgres database, and you can use your preferred tool. There is a Panteo or something like this to make business analytics. The tables are quite good documented, so you can use existing open source or not open source tool to go inside the database and make this activity outside. I'm use a couple of Python script to analyze the data inside. You know, Python has some driver for Postgres, so it's very easy. But I agree with you. If you need a more consistent business analytics reporting system, you can do this easily because you can access to the database and found the information. And this is the first version of AML inside Intel. The second version, if you count the very first Chroma version, and we are in the process to increase the number of metrics that we acquired and stored in the database. But we want to understand to don't confuse the user, because the intent of this software is to help administrator to manage easily. But we want to improve this tool to go a little bit deeply in some metrics that are useful for the user. For example, in my opinion, BRW stat is something that you can have on your monitor tool to understand the fragmentation of your OSTs, for understand the latency of your what's going on, and there is a couple of metrics that should be included in. But for business analytics, you can attach directly the software that you prefer. It's very easy.
Sorry. I would like to come back to the first part, to your metrics, and just generally ask: is there any comprehensive documentation about the meaning of all the stats you can find in the Brock file system? Because I'm still relying on Daniel Cobra's talk of last year to understand what is going on. I can run LAD stats, but what does it mean? So that.
Okay, all right. I suggest to you to open the code. No, I'm joking. No, right now we improve the manual. If you go to the Intel Wiki webpage, you find the documentation and the last build of the last version of the documentation. And we put an effort to document the stats of the clients. Now I saw a very good documentation on that, a very worse documentation on the metadata stats is not updated at the moment. Good documentation on the OSS stat. Okay, so we are in the process to improve this documentation. Help us to do that because it's open source. So if you can help us to improve but the client part is very well documented in the manual on the Intel Wiki page.
Actually, that's a really good point with the. Hi, that is a good point. I mean, you were just joking about the opening a ticket, but that's actually a really good thing to do. If you open a ticket against the LUDoc project in Jira, then if you know there's an area of the manual that could do with improving, we know there's a lot of areas that the manual could be improved in, but that signals that there's a particular one we can do and that someone cares about it, so it's more likely to get looked at more quickly. So if nothing else, not everyone's got time to write out the docs, but if you know there are no docs and you've had to struggle along, let us know and we'll, at least be aware that that's something we need to get to.
3 people of my group is involving to improve the documentation, but the documentation is very long and suffer of the history of Lustre. There are many 1.8 stuff, many 2.2, and now we put some highlight for new improvement in the 2.4. So. But it's useful. Any other question? Okay. Thank you.